This lecture is about wish dimension, and it is also a part of SVM. So SVM algorithm is looking for a line with maximum margin. Then why does the SVM algorithm look for linear line with a maximum margin? Why does it maximize margin? Okay, that is the question. So here we're gonna talk about that, why the maximizing margin is important, and we're gonna give you some theoretical background for that. So why do we care about maximizing margin in SVM? Webnik, who is kind of inventor of SVM algorithm, has proved the following theorem here. So in this theorem, H is what is called the wish dimension. So wish dimension H is less than or equal to minimum of these 2 plus 1. So here the D is diameter of smallest sphere of data, and M0 is the dimensionality of data. So for now, you can assume once data is given, you can assume this D value and M0 is fixed, okay, kind of constant once data is given. So what matter is this rho, which is the size of margin, okay. So if this rho margin goes up, okay, then if this goes up, this value goes down, and then that means this H goes down, okay. So if this increases, this decreases. On the other hand, and the rho margin goes down, decreases, it's gonna increase this, and actually you're gonna increase this H as well, right? So if increase this, if we increase this, then you're gonna decrease this, you're gonna decrease this, then you're gonna increase this, okay. It goes in opposite way, okay. So that is the bottom line. So if you maximize the margin rho, then actually you're gonna minimize the value of H, wish dimension. If you maximize margin, you're gonna minimize wish dimension. That's the conclusion of this slide, okay. Then you may wonder why, what is wish dimension is, why is it important to minimize wish dimension? So we're gonna talk about this in the rest of the slide. Before we move on to wish dimension, let's talk about the flexibility or capability of classifier. So when we say a classifier is very flexible or capable, it means that classifier can represent very complex concept or very complicated classification boundaries. So that's the definition of flexibility or capability of classifier. So then the next question is, what kind of classifier is very flexible? So in general, people say the classifier with many parameters is flexible and capable. So that means we have a classifier and it contains many parameters. Usually we believe that classifier can represent very complex concept or very complicated classification boundaries, etc. Okay. But actually, this is not always correct, and there are some exceptions. And if you look down here, let's say we have a function which is a sine curve here, a times sine bx. This is phase, and this is a period. So this function has only 2 parameters, a and b. So even though this one has only 2 parameters, actually it can represent any arbitrary combination of class values in this one-dimensional data. So we have one-dimensional data, and this data can have any arbitrary combination of class values. Then by using this function, you can, by adjusting these a and b values carefully, you can discriminate these data correctly. Okay, so the conclusion here is even sometimes the function classifier with very small parameters can be very complex, very flexible, very capable. Okay, can represent very complex things like this. Okay, so number of parameters is not a good choice to measure the degree of flexibility or capability of classifiers. Then what else do we have? Bepnik says, so it's not number of parameters, okay, which determines the flexibility of classifier. And we have something else, and it is called a Boise dimension. So Bepnik says instead of number of parameters, and the flexibility of classifier is determined by Boise dimension of the classifier. Okay, so actually the Boise dimension is the measure which determines the degree of flexibility of classifier. Okay, so if a classifier has very high dimension, it means that class is very flexible, very capable, and it can represent very complex concept. And if classifier has very low Boise dimension, and then the classifier is very simple, very not flexible, not very capable. Okay, so that's the definition of Boise dimension. Now we need to know the definition of shattering. The definition of shattering is as follows. Let's say we have classifier F, and also we have R data points x1, x2, xr, and each data point comes with a class label y1, y2, yr. Okay, and then we say a classifier F shatters these data points if and only if for every possible labeling of data, for every possible labeling of y, we have many class value y. For every possible combination of y values, this classifier F can correctly classify them. Okay, if that is the case, we say this classifier shatters these data points. That is the definition of shattering. So before we move on to this example, let's take a look at this one here. So I said here, for every possible labeling of y values, so let's say we have all data points, okay, then we have all class labels. And so I said for every possible labeling of y, then we have 2 to the power of r labeling combinations, right? Because we have r y values and we have r data. So we have 2 to the power of r's labeling combinations. By the way, we assume these y values are binary, okay, +1 or -1, okay? So we have, when you have r data, we have 2 to the power of r class label combinations. So let's take a look at an example here. Let's say for this classifier F, let's assume this classifier F is linear classifier. This means, which means line, okay? We have this classifier is linear line, linear classifier. And let's say we have 3 data points, x1, x2, and x3. We have only 3 data, and classifier is linear, okay? Then you're going to show that this classifier, linear classifier, can shatter 3 data points. Then by definition, we have 3 data points, and for every possible combination of y values, these classifiers must classify them correctly, right? So because there are 3 data points, we have actually 8 different combinations of class values. Here, everything is minus. And here, this plus, minus, 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 plus, all the way here is everything is plus, okay? Because there are 3 points, 2 to the 3s, okay? It means 8 different combination of class values, right? And the classifier here for the classifier, we assumed it is linear classifier, so that means line. So in this case, everything is minus. You can draw line somewhere like this, okay? So here, this line actually correctly classifies every data, okay? In this case, this is plus, this is minus. If you draw line here, okay, then we are good, right? This classifier correctly classifies plus and minus. In this case, you draw line here, it's fine. In this case, draw line here, line here, line here, line here, line here, okay? So in this case, if its classifier is linear line, and we have 3 data points, for every 8 possible combination, then this classifier, linear line, can classify them correctly. So in this case, that means for every possible, combination of labeling here, it can classify correctly. Okay, so this is good here. So in this case, we say this linear line, this linear classifier shatters these 3 data points. That's definition of shattering. Okay. How about we increase the number of data to 4? Okay. Let's say we have 4 data points. Okay. Then this linear line, linear classifier, cannot shatter 4 data points because we have one example here, and let's say this is plus, minus, minus, plus, and then we cannot correctly classify using linear line. It's impossible, right? So by definition of shattering, this linear line cannot shatter 4 points because in this particular case, it cannot correctly classify these 4 data points, right? So for linear classifier, it can shatter 3 data points, and but for linear classifier cannot shatter 4 data points. Okay, that's the definition of shattering. So now let's define the definition of Cauchy dimension. As we have seen earlier, the Cauchy dimension represents the expressive power or flexibility of classifier F. So here comes the definition of Cauchy dimension. Suppose we have classifier F. The Cauchy dimension of the classifier is defined as the maximum number of data points that can be shattered by F. So let's take a look example here. So in last slide, okay, we have seen a linear classifier and we have seen 3 data point. So in that case, that linear classifier could shatter 3 data points. Okay, so linear classifier could shatter 3 data points, but also we could see that the linear classifier could not shatter 4 data points. Okay, so the maximum number of data points which can be shattered by this linear classifier is 3. Okay, so in this case, the Cauchy dimension of linear classifier is 3. Okay, because for the case of linear classifier, it could shatter 3 data points. Okay, but it could not shatter 4 data points. So that's why the maximum number of data points which can be shattered is 3. So that's why this Cauchy dimension of linear classifier is 3. Let's take a look at another example. Let's say we have an instance-based algorithm, nearest neighbor classifier, but the Cauchy dimension of instance-based learning or nearest neighbor classifier is actually infinity. Infinity means this algorithm, okay, instance-based learning algorithm is very high. It is very flexible. It can represent very complex concepts or very capable. Okay, so we can say that the higher the Cauchy dimension is, the more flexible or capable a classifier is. However, this Cauchy dimension is actually very theoretical concept, and for the most classifier, the Bayesian dimension actually is very difficult to be computed exactly. Okay. For the case of linear classifier, we could easily compute its Bayesian dimension. Okay, you can see its Bayesian dimension is 3. But in many other machine learning algorithms, actually it is very, very difficult to compute the Bayesian dimension of the algorithm. Okay. So roughly speaking, if you think the classifier is flexible, then roughly speaking, you can say, okay, it probably has a high Bayesian dimension. Okay. So why do we care about the Bayesian dimension in the first place? The reason is by using this Bayesian dimension, we can actually estimate the upper bound of test error of the classifier. That's the reason. Okay, and SRM represents the structural risk minimization, and basically what SRM means is when you train a classifier, you should minimize two things. The first one is training error. That's obvious, okay? And second thing is you should also minimize what is called regularization term. Regularization term is a function of flexibility, or you can say a function of Bayesian dimension. Okay, again, Bayesian dimension is the measure of flexibility. So regularization term is a function of Bayesian dimension. So you have to minimize training error, and also at the same time you have to minimize the regularization term. It represents the complexity of a model. Okay, it's flexibility of a model. And this one here is the specific formula of SRM. So we have test error and training error, and test error is what matters. Training error is the size of error when you train a classifier, okay? And what really matters is this test error. Okay, test error is the error of future data, okay? It's the error of data we have not seen before. So this is what matters. So test error is less than or equal to a training error plus this one. This one is regularization term. Okay, so when you train them, you actually minimize training error, and also at the same time you have to minimize this regularization term. If you look carefully here, regularization term is a function of h, which is Bayesian dimension. H is Bayesian dimension. And in this case, capital N is number of data, and this eta is constant related to confidence level. Okay, so this is a constant, and N is constant. So if H, Bayesian dimension, goes up, actually this term goes up, and that means test error may go up, right? And if H decreases, this decreases the whole term, regularization term, and actually that reduces the test error. Okay, so if your classifier and the classifier, the Bayesian dimension of classifier is very low, actually it reduces its test error. Okay, that's why we compute Bayesian dimension. So finally, if you go back to the beginning of this chapter, the question was, why do we maximize margin of line, okay, in SVM, right? So the reason is, if you maximize the margin of line, then it actually minimizes the Bayesian dimension of the classifier, okay? Then if you minimize the Bayesian dimension, that if you look at this formula, if you minimize Bayesian dimension, actually it reduces test error, okay? So if you look for a line with a maximum margin, it actually reduces the test error of the classifier. That's why we are looking for a line with the maximum margin in SVM. This slide shows the importance of Bush dimension and the regularization term. So roughly speaking, as I said, simpler models have smaller Bush dimension. And in decision tree, we have learned pruning in decision tree. And actually, the pruning in decision tree is the process of reducing Bush dimension of decision tree. So pruning decision tree makes the tree smaller, compact, simpler, right? So by doing so, you can reduce the Bush dimension of decision tree. That's what we did in decision tree. So suppose we have two classifier, classifier 1 and classifier 2, and this one here is training error of classifier 1, and this is training error of classifier 2. So this one has smaller training error. Classifier 1 has smaller training error than classifier 2 has, right? This shows the range of test error, okay? And again, this one shows the range of test error. So if you compare these two classifier 1 and classifier 2, so even though the training error for classifier 1, even though this training error is smaller than classifier 2, actually you're going to be better off to choose classifier 2, because what matters is test error, and this is the range of test error, and this is the range of test error. So actually the maximum boundary of test error for the case of classifier 2, it has a smaller boundary of test error than classifier 1. Okay, so if you compare these two, it's much better to choose classifier 2 instead of classifier 1. Okay, even though its training error is worse than the training error of classifier 1, it's actually, you can say classifier 2 is going to show better performance in the future because its test error has lower boundary. And this one shows the relationship between this is Bush dimension and training error, and this is the regularization term, also known as Bush complexity term. So as the Bush dimension increases, training error becomes smaller, lower, okay? And as the Bush dimension increases, of course, the Bush complexity, the regularization term increases like this. So based on SRM, you have to minimize both of these terms. Okay, you have to minimize training error and also at the same time this Bush complexity term. So when you train a classifier, you have to minimize these two terms simultaneously. Okay, so if you add the error, these two errors together, this is the summation of these two graphs. Okay, something like this. So the optimal Bush dimension should be somewhere. Optimal the complexity of your model should be somewhere around here. Okay, because you have to minimize these two terms together. So this is the optimal Bush dimension. The complexity of model is right here. Okay, that's a structural risk minimization.